Okay, so AES Power Analysis, that's what we're going to talk about today. So let's first start off what is power analysis? So it's when you like record the power that some device uses, and then you analyze that to try to recover some information about it. So you often record power and it looks something like this. In this case, this is AES, which does 11 rounds. AES 128, which does 11 rounds. We'll talk about what that means later. But you can see the 11 dips if you actually count them, or you can just believe it. But there's 11 dips there. And so that's a simple power analysis where you just like look at it and you see it does 11 things. So that must mean there's 11 things going on. What we're going to be talking about is a little bit more complicated than that. So first, let's start off with how you record power traces. So it's just a black box device. It's literally a black box. We're going to be doing it on the AT Mega 320p. 328p, it doesn't actually matter what you do it on, but that's what we're going to be doing. And one important thing is power is current times voltage. That's how you calculate it. So this is our setup. There's a lot going on here. AT Mega 328p, that's the device we're measuring the power of. The thing in the top left is an oscilloscope, which measures voltage per time. So like every X amount of seconds or microseconds or nanoseconds or whatever, it will record the voltage that it measures on the probe and record it. So you'll end up getting something like that, where it's some amount of voltage per time. Let's go back to it. So it's just going to measure the voltage at the VCC is the voltage that the device is, where it's getting its power from. So this setup won't actually work. We'll talk about why that won't work in a second. VCC, the thing next to it, is the power supply or like a battery or something like that. That's just the notation. Ground is 0 volts. It's just the reference that you base everything off. And what we're going to be doing is we're going to send some data to the AT Mega 328p. It's going to encrypt it, and it's going to send it back. And we're going to record the power usage during that. The trigger line is every time it encrypts something, that's going to go high, and it's going to trigger the oscilloscope to start recording. And then when it's done, it's going to go back down. So that way we know, we're making it easier on ourselves because we're going to know where it's encrypting. Power equals I times V. Here we're just measuring voltage, so we need a way to get the current. And the way we do that is we add a resistor right there. The R, it's the squiggle. The equation in the top right, it's basically saying the voltage across the resistor is the voltage on one side minus the voltage on the other. If you look at the resistor, VCC is on one side, V's one's on the other. The second equation, that's called Ohm's law. It's basically just, it's true. It says that the current through a resistor is going to be the voltage across it divided by the resistance. And we're going to use those two equations to calculate the power. Because now we have IR, and the power on the bottom is the power of the device, not the power of the resistor. And we're going to go through the math of how we do that. Step 1, we got the current from the resistor from the last setup, and the voltage of the resistor from the last setup. So the current through the resistor is going to be the voltage across the resistor over the resistance. The power of the device is going to be that current times V1. V1 is the voltage we're recording on the oscilloscope. So in the fourth step, everything, we know VCC because that's the battery. We know V1 because we're recording that, and we know R because we put that resistor in there. So now we can calculate the power. So when you record it, it's going to end up looking something like this. Not really useful because it just looks like noise. So now,
yeah, now it makes sense.
So when you put in code, it'll look like an array like this. A bunch of numbers in an array. Nothing really special about them, but it's just how to visualize how we're storing that data. So now let's get into AES before we get into how we're going to analyze the power. AES, it takes 16-byte plaintext, and then 16-byte, and then, yes, 16-byte plaintext, and outputs 16-byte ciphertext. It also takes a 16-byte key, kind of. We're going to use the one that only uses the 16-byte key. One thing to know is you put in 16 bytes, you get out 16 bytes, and those 16 bytes look random. It's not, and we're going to assume that we can't break something in AES to try to reverse that operation. Our goal is to recover the key given either the plaintext or the ciphertext. We're going to use only the plaintext today, but you can also do it with the ciphertext. There's allowed key sizes 128-bit, which is 16 bytes, 192 and 256. Let's go into how 128 works. The first step is key expansion. We'll go into what that does, but it just generates a bunch of keys for the 11 rounds that happen in AES. The initial round key, which does an add round key, which is basically XOR plaintext with the key. That's what we're going to end up attacking later. It does 9 rounds of sub-bytes, shift rows, mixed columns, add round key. It's just a bunch of stuff. For this attack, we don't really need to know too much about it. And then the final round does sub-bytes, shift rows, add key. So let's go into what the key expansion looks like. It just generates round keys. So for the first round key, it's going to be the original key that's given. And that's important for our attack later. And then just does a bunch of math and stuff to generate the next 9. We don't really need to know that. Sub-bytes, that's going to be like a lookup table type thing. So you're going to have a byte, and there's going to be a giant array. And that byte, when you index into that array, the value that is at that index is going to be the replacement. This is the operation we're going to end up attacking. This is what the table looks like. So say you had the byte FF. You go to F on that axis, F on the other one, and your output would be 16. In hex, that is. So that's really all it is. Shift rows, mix around the columns because why not? Or mixed rows because why not? It basically just shifts rows over, except the first one, or like a rotate. Not too important for this attack, but it does it. Mixed column, you basically multiply the matrix by another matrix of constants. Not too important in this attack, but it's a thing that happens. Add round key, this is important. So what add round key is, you XOR the round key and the state. The important thing to note is for the initial round key, add round key, the round key is going to be the initial key that we feed into AES, and then the state is going to be the plaintext that we feed into AES. So it's two things that we know. Without, well, we don't know the key. We know the plaintext, and that's important. But it's one thing we don't know, which helps simplify things. So this is what it looks like all together. We first have our initial round key, which is our key and the plaintext. We know the plaintext. We just don't know the key. Then we do the key expansion for all the other keys. You can do it in parallel with those loops, but yes.
So I'll let you finish this slide.
Okay, and then we have the 9 rounds. It just loops through that 9 times. And then the final round. Yeah.
What's a mux?
A mux. It's a multiplexer. Basically, you have 2 inputs on a thing, and you're able to select which one you want to go through. So for the first round in the 9 rounds, we would select the thing on the right. And then for the rest, we'd select the thing on the left, because it's kind of like feeding back into this loop. So how do we get into the analysis of this? So our goal is to recover the key. But how do we get the key out of a bunch of numbers? Well, we have to relate some operation that happens in AES to the power usage that uses the key in that operation. And what we're going to go for is the initial add round key and the sub-bytes. So that add round key is just an XOR, which is exclusive OR. Is everyone familiar with that? Okay. It's that circle with the X. So we know M, we don't know K, but we know what the S box is, and that's what we're going to attack. We're going to attack what comes out of that S box. So there's two main power analysis attacks, differential power analysis, or DPA, and correlation power analysis, or CPA. Not certified public accountant, but same thing, not really. Correlation power analysis. We're not going to do a DPA because it's a bit more inefficient, and it also has some like weird things where you'll only use one bit instead of all the bits, and it kind of adds, it creates more false positives, and it's also a lot slower. So first we need to develop a power model of the device. We're going to be using the Hamming weight power model. We'll get into what that is later. And then we're going to need to compare that power model to the measured values. And we're going to use Pearson's correlation coefficient. It's a big equation. We'll get into it and see it's actually not that bad. Maximum correlation, when we maximize the correlation, that is the most likely key. That's not always right, depending on how good your data is. I actually tried to measure some stuff in the lab, and then I realized my setup was wrong, and I wasn't able to recover the key. I got one byte, but not the whole thing. But I found some other traces online with people like a really good setup, and it works. So let's talk about what the Hamming weight is. The Hamming weight of like a bit string is just the number of ones there are. So in this bottom thing, there's 3 ones. So the Hamming weight is 3. It's not that complicated. But so what we're going to do is find the Hamming weight of our plain text, which we know, our guess of the key, which is I. So yeah, we're going to XOR that, our plain text and our guess of the key. We're going to feed that into the S box and get the Hamming weight of that, and that's going to be our power model. Yeah?
What is the S box?
It's that big thing, this big thing. It's just defined in AES, and it's just a lookup table, kind of.
And we can easily get how do we get the stuff out of the S box? Like, how do we interrupt AES midway through to get?
We're not. We know the S box, so we're going to calculate this on our own.
Okay.
We know the plain text. We're going to guess a key.
Oh.
And then we're going to run that through the S box, and the Hamming weight of that is our power model. So this Pearson's correlation coefficient, it basically describes how related 2 variables are. So it's going to be between, its output is going to be between -1 and 1. 0, greater than 0 if they're related, like if one increases, the other one increases, directly related. It's going to be less than 0 if they're inversely related, and 0 if they're not related. That's not really too important. We just care mostly about what's going to give us the highest magnitude out of that, because we want to find what's most correlated to our stuff. So H is going to be our power model estimate, the Hamming weight thing. T is the measured value. D is the trace number. J is the point number. So that trace is made up of a bunch of points, like we saw in that array. And J is going to be the index into that array that is our trace, which is the values measured over time. I is going to be our key guess. Yes. And D is the number of traces. So basically, we're going to take the difference between, oh, and the H bar is the mean of H's. So we're going to take our power model estimate of a certain trace of a certain key guess. And then we're going to subtract that from the mean of all, we're going to subtract that from the mean of all power model estimates for all keys. And we're basically going to, that's the HDI minus H bar I. We're going to do that for the power traces. And then we're just going to square the things on the bottom, multiply them in square root. So let's go, let me show you how this like actually looks in code, because it's a lot easier to understand. Here we go.
Wow, that was.
Let me.
Yes.
Yes.
I feel everything is so elucidating.
Control plus. I think that's the thing. Yes. No. Is that big enough? Okay. So we're gonna import some stuff. The Hamming weight lookup table. We're just gonna generate a lookup table for all bytes. That is the Hamming weight, so we don't have to calculate it each time. It just makes some things faster. VCC is going to be our constant, which is the voltage we supplied to the device. It's whatever you do in your setup. We happen to do 3.3. R is going to be our resistance, which is that resistor we added. We just happen to use 150. Yeah.
Does tuning the voltage supply to the resistor improve or reduce the quality of traces?
Kind of. You usually go for the smallest resistance you can get, where the devices that you're using that can measure can still see a difference. Yeah.
So is that resistor value, is that a nominal 150 or is that like actually measured?
It actually doesn't matter, so we're going to end up calculating the power, and we'll see that equation that we used, the power is proportional to the voltage that we measured. So we can actually just not do that calculation, just use the voltages, because you're just trying to maximize the correlation between the two things and not the actual values. So it actually doesn't really matter. And it's the one that 150 is the stuff you'd read off the bands on the resistor. Yeah. This is our S box. We'll use that for calculations. This line right here, we're using a library. It's going to load some traces from some magical file structure. And it's just going to give us an array of arrays of points. Yeah, so like index 0 would be one big array of the first trace of our first test. This is going to be a bunch of plain text, this line, that is just correlated to each trace. So index 0 VCC traces is going to correspond to the plain text of plain text index 0. We're going to calculate all the power in that loop. We don't actually have to do that because point is proportional to temp, and the correlation kind of accounts for that, because we're just trying to maximize correlation and not the actual values. We're gonna assume all the traces have the same number of points. You don't have to do that. It just makes some of the code later on a bit more complicated in the length these lines. And then we're gonna create an array for our recovered key, or our best guess. So for each byte in the key, we're gonna go through each byte in the key and guess a key. So here we create an array for the results of that correlation coefficient. And then here we create another array. It's just where we're gonna store stuff. So let's go to where we actually do some math. So for each key guess, 0 to 256, ignore the TQDM up there. It just makes the output look pretty. So we're gonna go through each key, each possible key. And for each possible key, we're gonna calculate the power model using the Hamming weight, which is right here. Power model trace num equals HW. So what we're doing is we're XORing our plain text, which we know, with our key guess, throwing it through the S box, and calculating the Hamming weight. And that's our power model. So we're going to do that for each trace.
Can you explain one more time what a power model is?
It's just something we're trying to say, this model is going to increase with the amount of power this device is using.
Oh, so it's our thing that we're correlating to power.
Yes. We're going to say, since there's a bunch of ones, it's going to use more power.
Oh, I see.
Yes. Mm-hmm. So here we take the mean, which is the h bar. And that's of our expected power usage. And then we're going to take the mean of the points, which is the t bar, in that big equation right there. So for each key guess, go through each trace and generate your expected power model. And then for each trace, again, within that same key guess, you're going to sum up the difference between the power model of that trace with the mean, and then sum up the difference of that power trace minus the mean of all traces. And what's that going to, that's going to calculate the t minus t bar. We're going to sum those up. And then ultimately, we're going to throw it in this array for that key guess. So what we're doing here is that numerator thing. Numerator is the top part of this equation. It's the h difference times the t difference. And then we're going to take the square root of the denominator parts multiplied. And that's just the definition of Pearson's correlation coefficient. And then ultimately after that, we're going to find, so what you're going to end up doing is correlating each point in each trace, each point in the trace to the power used. So at a few of those points is going to be where the S-box operation actually happens. And that's where it's going to be maximized. So we have to find the max of that entire guess. We have to find the max of the trace of the correlations. That's a lot of words. So basically, our trace is something like that. And then for each of these points, we're going to correlate it with its expected power usage. So we're going to end up getting another, for each point we're going to find like its correlation. So maybe you'll do something like that. And then at some point it's going to spike, and then it's going to go like that. Because a bunch of this is just noise, because it's not that it's not the S-box lookup that we're targeting. And then this point is going to be that S-box lookup. That's what CPA output is. CPA output key guess is. It's just a giant array of points. And we're going to find the max, which is probably where that S-box is. We don't actually care where it happens. We just want the highest correlation, because that's going to give us our key guess. Yeah. So that brings us down to the max CPA, which is here. It's just that max point. And that's going to be, for that key guess, that's our maximum correlation. So we're going to go through all key guesses and find a maximum correlation for each key guess. Then at the end of that, we're going to say that byte of the key, we're going to find the max of all those maxes. And then we're going to say that's our key guess. Then we're going to go to the next byte and do all that again. And the next byte and do all that again until we have 16 bytes. And basically when you run this, you get something that looks like that. And so the TQDM is what makes the 100% and stuff like that. So it's going to run through that. It's going to guess the byte, which is 98 in the first one. This is correct. I can show you the actual key. Let's stop this. So that's the actual key. As we can see, it's actually recovering the proper key. And that's pretty much it. I know there's a lot, so if you have questions, go ahead and ask if you're not sure about anything.